Welcome back to ECE 442-542. Just as way of announcements, we have homework number 7 is due on a different day than normal. It will be due on a Saturday, just so that you're not turning it in on a Sunday or a Monday during the last week of school. Trying to abide by the rules. So our homework number 7 will be due on the 29th. That's a couple of days before design day. I'm sure that's more what you're focused on anyway. The project is due, it is actually due on the last day of class, the 3rd. And teacher course evaluations, you're probably getting inundated with emails on those. Those are due on the last day of class also. Final exam is scheduled for Thursday on the 11th, and that's from 1 to 3. Is that the last homework you should expect? No. Homework 8 will be for extra credit, and it will be due a little bit later than this. Well, it's extra credit, so it's not a mandated turn-in assignment. So I'm squeezing one in that way. Today what I want to do is go through and finish up our rules for the root locus, rules 4 and 5, and we'll do that or try to illustrate that with some examples. Here's our standard block diagram, and I've now, if we have any poles and zeros in the controller, we've collected all of those into what I'm now labeling as G bar of Z. So we have little n pole factors. We have little m zero factors. And what we're trying to do now is play with K to move the closed loop poles around in our Z-plane. And we now have rule number 4, and I'm just going to state that. It's a little bit long, but you can write all this down later, possibly. I just want you to understand it. Rule number 4 is really concerned with guidelines, or lines that are helping you sketch your root locus. And rule number 4 talks about the asymptote lines. You've already actually used asymptotes when we had a pole zero excess of 2 and our infinite zeros were at plus and minus 90 degrees. We were actually using this rule, but we hadn't yet applied it or introduced it. It becomes more interesting when we have a pole zero excess of 3 or more. And then we have angles of 60 degrees, etc., for the asymptotes that are our guidelines. But rule number 4 says that these are asymptote lines for sketching the branches of the root locus associated with the zeros at infinity, or those zeros that are going off to infinity, and how many of those we have depends on the pole zero excess. There's one key feature that you want to keep track of, and that is this pole zero excess. I'm labeling it or denoting it PZ sub E. That will just be the number of zeros at infinity, or if you look at the number of poles you have minus the number of finite zeros, that's your PZ sub E, or your pole zero excess. Once you have that, then you can start calculating these asymptote angles. These are the angles that these guidelines make with the real axis, and we can find the center of where those guidelines are located along the real axis. The angles are given by essentially 180 degrees divided by the pole zero excess, and then we just march through that in terms of particular values suggested by 2L plus 1, where L varies from 0, 1, up to 1 less than the pole zero excess. That will give us all of our asymptote angles. And then the centroid of those guidelines are determined by summing all of your poles, subtracting all of your zeros, finite zeros, and dividing by the pole zero excess. as an example, and we'll work through this a little bit more thoroughly later, but just to give you a feel, here's one pole zero pattern to try to help illustrate this concept of rule number 4. How many poles do you see on the z-plane? 3. These are tough questions after a long weekend, or never mind. Now, what branches, how many root locus branches should we expect? 3. So now we're stuck on 3. We should expect 3 root locus branches. How many zeros at infinity do we have? 3. We're stuck on 3 because how many finite zeros do we have? None. We have 3 poles, no zeros. Our pole zero excess is 3. We have 3 zeros at infinity. And which, if we subdivided this infinitely long real axis, how many segments would belong to the root locus? I'm sorry, how many? I'll let your answer be correct. How many ways have we cut the bread? Okay, we've cut the bread into 3 pieces, right? Because those 2 poles at the origin are on top of each other. We now have 3 real line segments. How many of those segments belong to the root locus? Now we don't want 3, we want 2, don't we? We have, if we were standing where that red dot is, how many poles and zeros are to the right of that location? 1. That's an odd number, so we know that all poles, I'm sorry, this is a section of the real line that belongs to the root locus. We have this pole here, and I don't even have to know where that is. And we have one of these 2 poles at the origin going right. Now, if I was standing in the left half plane, this is the, let's just say this is the z-plane. It really doesn't matter, so I'm not even going to say. But now if we are in the left half plane, how many poles and zeros are to the right of that position on the real line in the left half plane? 3. 3, thank you. So now that we have 3, that's odd. We know that the entire negative real line is belonging to the root locus. As we crank up the gain k, one of the poles at the origin and the pole in the right half plane will come together and they will break away. They're not going to break away at the midpoint between those 2. We'll have to figure out what that breakaway is by finding the relative maximum of the gain in that segment of z. But now they break away, but this dot that I've indicated right there is the centroid of my asymptote lines, and this phi sub a is going to be how big? How big is that angle, phi sub a, if we plugged in L equals 0 using this pole 0 pattern? And don't say 3. So now we have 180 divided by 3, right? So the fundamental angle, that phi sub a, is 60 degrees. These 2 branches will break away somewhere, but one will go towards that asymptote and the other will approach that asymptote as k goes to infinity. That's what rule number 4 allows us to understand. It tells us where, and where's the other asymptote? It's going off to minus infinity, or it's at 180 degrees. We have 3 asymptote angles. The fundamental, which is when L is equal to 0, is 60 degrees. That's the one I usually emphasize. Then we have another one at 180, and we have another one at 300. But if you have a pole 0 excess of 3, you're now splitting a circle into 3 equal wedges. And so now don't you just wish you had a piece of pie or a piece of pizza that big? That would be divided by 3. So now we know that those are now 120, those asymptotes are 120 degrees away from each other. Yes?
Do those two conjugate poles still break away at the origin?
So now the two poles at the origin, one is going right and one is going left, right at k equals 0. As we crank up the gain k a little bit beyond k equals 0, one goes right and one goes left. They stay on the real line. They don't.
It's not like it's not curved or anything?
There's nothing curved at the origin. They're staying on the real line. One goes right and one goes left. The only curvature happens after the break between the one at the origin and the one in the right half plane. Yes? So these asymptotes are not a part of the root locus. They are simply guidelines to help guide the sketching of your root locus. Those dashed lines are simply guidelines, but they are informed by rule number 4. So the red lines will approach those asymptotes. And in our earlier example, when we were doing a breakaway, when we had a pole zero excess of 2, our asymptotes were in fact on the root locus. But when we have a pole zero excess bigger than 2, then we are approaching those asymptotes with our root locus branches that are going off to infinity. That's rule number 4. And we'll come back to that with an example, but I want to make sure that we get rule number 5 before we go any further. Rule number 5 talks about if we now have complex poles or complex zeros. If we have complex poles or complex zeros, then we have root locus branches starting on the poles, or if there are zeros, ending on those finite zeros. Rule number 5 is concerned with the direction or the angle that the root locus leaves the poles or approaches the zeros. And they will then be called departure angles for the poles and arrival angles for the zeros. And we want to know, just to give us a feel for how the root locus is departing or approaching those poles and zeros respectively, what are the angles? And the angles, as always, are measured with a virtual horizontal line extending to the right. Okay? Luckily, you're just listening to this and not watching the video of this, but something is extending to the right. Here are some examples of that. And I want you to make sure that it's clear what we're doing. In the first one on the left, how many segments of the real line have we cut with our poles and zeros? Or how many real line segments do we have in that leftmost picture? Okay, now it is getting tiring. But we have 2, right? We just have one singularity on the real line. It's the 0. So we've now split the real line into a positive half and a negative half. Do any of those line segments belong to the root locus? Yes, if we're standing in the left half plane, we have an odd number of poles and zeros to our right. So we know that if you were looking for partial credit, you could put one of the branches. How many branches do you have in this leftmost plot? 2, because you have 2 poles. Now, what we're trying to determine with rule number 5 is how the root locus is leaving or departing from those poles. And it will be symmetric. It will be symmetric relative to the real line. What happens upstairs is going to be mirror imaged downstairs. So we really just need to know what's happening upstairs. And we're now saying what's going to happen with the root locus. And in fact, you can anticipate what's going to happen. If you know where this pole is and you know the zeros at the origin, you can find that radius. Once you have that radius, you're now good to go relative to knowing the structure of 2 poles and one 0. In this case, you now have this radius there, and using your compass, that would be, well, if that was a circle, that's supposed to be a circle. The bottom one looks a little bit better than the top one, so let me, well, okay, that's up for debate. But you're departing from the pole, the two poles, you re-enter, and you're re-entering a radius away from the origin, and this departure angle is actually measured, what was I calling it? I was calling it alpha sub d. That's the departure angle. So rule number 5 is going to tell us what that angle is, alpha sub d. Can I use a different color for what? For the different branches? Well, let's say that this one is highlighted. It could go this way or it could go in, but now we have this one doing the mirror image, except when it gets there, now it's going that way. Does that help? So we have two branches on the root locus, and this picture is telling us what? Let's not lose track of what this root locus is really doing. This is showing the possible closed loop pole pattern, or the possible values for our closed loop poles for this combination of poles and zeros in our transfer function consisting of the plant and the controller. So for this combination of pole and zero, we can now have these closed loop poles, and that we can find a particular location by adjusting the gain k to a certain value. What if we move over to the right picture? Now what do we have? How many real line segments are there? There's now 4, and we can put one here and one there. Is that correct? What's my pole zero excess? 1. So what's my asymptote angle? 180 divided by 1, it's 180. So the only 0 at infinity is going off to minus infinity. Everything else is going to terminate in the finite z-plane. What's going to happen between my right two poles? How many branches do I have on that real line segment? Deep breathing. There's 2, correct? We have 2 poles. They're separate or leaving the poles. One's going right, one's going left. They break away at the relative maximum between those two, and it's not going to be necessarily equally spaced between those two because you have all these other poles and zeros. But in a quick sketch, you might just say, okay, I'm going to assume it's there. Ooh, that's supposed to be a mirror image, and this is going to now be maybe, okay, give me a break. It's a Monday afternoon. But we now have, you can draw better. Fine. What's the angle of arrival? The angle of arrival is now measured with this virtual horizontal line, and we now have this tangent to the root locus as it arrives at that 0, and now I'll call this alpha sub a. And if we calculate alpha sub a, you can quickly sketch that root locus diagram. If you calculated alpha sub a and it came out to be 0, you know how you're coming in. You're coming in at a horizontal tangent. If you calculated it phi sub a being 90, now you know you're coming straight down from the top. If you calculated phi sub a and it came in as 135, now you know you're kind of going beyond and coming back in at 135 degrees. If it was 45 degrees, you're coming in halfway between horizontal and vertical. Never mind. I won't try 45 degrees. Well, I guess I could. I locked the wheels before I started today's lecture, which is a good thing. Questions on Rule 5. We're trying to figure out how we're departing, the angle we're departing complex poles, and how are we arriving at what angle or what direction at the complex zeros. Question? Okay, so now the question is, what if I think this is the question, what if my angle actually ended up being 135? Then I'm highlighting a hypothetical, and the question was, how far out do you go before you start returning? That you would just have to, you could calculate. You could, depending on what you wanted, you could now let MATLAB do this more precisely, but in fact, you would probably be able to do something like that. These should be sort of nice looking curves if you drew them properly. Thought somebody was commenting on my curves. Okay, any other questions on these root locus diagrams? Let's look at rule number 4. Or in fact, trying to develop where this might be coming from. Suppose that you had a pole zero pattern that had a pole here, a zero here, and 2 poles there that were complex, and this is now the z-plane. And you want to now go far, far away from that finite location in the z-plane, and you want to know what happens to the root locus far, far away. Or far away from this pole zero pattern, what does the pole zero pattern look like? Meaning, if you are now, if that's the z-plane, and now you went clear over here and looked back, what would that pole zero collection look like? Effectively, if you went quite a ways away from that pole zero diagram in the z-plane, what would it effectively look like? What would the approximate behavior of 3 poles and a zero look like? I think that's a TV show, isn't it? 3 poles and a zero? I don't know. It just sounded like a TV show. 3 poles and a zero. So what do 3 poles and a zero, 3 finite poles and 1 finite zero look like? Far away. If you went far away, wouldn't that, in a sense, just look like 2 poles centered somewhere, effectively? Wouldn't it somewhat look like that? Let's say this is now the approximate behavior. Meaning, what's our pole zero excess? We have 3 poles and 1 zero. So effectively, we have 2 poles. And that's what it's going to look like if we're way far away from that finite region. It's going to look like 2 poles centered somewhere that is a centroid relative to the distribution of those finite poles and zeros. Where they are located, we'll say, is at the centroid, And in terms of if these are now two poles and you had to sketch the root locus for this, what would you do? If you had to sketch the root locus diagram for this pattern of poles and zeros, what would it look like? This would just be our standard plus and minus 90, would it not? Because there's an even number of poles right on top of each other, so no part of the real line belongs on the root locus. As soon as you start changing the gain k, they would have to go off the real line. And so you could think then that this one of these has an angle theta p1. If we just picked a point there in the z-plane and measured the angle from that pole to that point, it would be theta p1. The other one would be theta sub p sub 2. Or effectively, we have something that looks like 1 over z minus sigma sub a. Really, it's sigma sub a squared, isn't it? And what's the angle? From our phase angle condition, we know that the sum of the zero angles minus the sum of the pole angles have to equal minus 180. How many zeros do we have? None. We have an angle due to one of the poles. The other pole, we're subtracting those, and that has to now be 180 degrees. So that now this is really theta p1 and theta p2 are exactly the same. So we now have minus 2 theta p1 is equal to minus 180 degrees. Or in this case, theta p1 is equal to what I was calling now the fundamental asymptote angle, phi sub a, which is 180 degrees divided by 2, or 90 degrees. And the general formula for the centroid, or where are those asymptotes centered on the real line, so let me just say that this is now the real line or real axis point where the asymptotes are centered. Is given now. We have to account for all of those finite poles and zeros. We now have to take the sum of the poles minus the sum of the zeros and divide by the pole zero excess. That's sigma sub a, and the angles of those asymptotes are 2L plus 1 times 180 degrees divided by the pole zero excess, and L now varies from 0 to 1 up to 1 less than the pole zero excess. Let's use a specific numerical example to help illustrate that. Suppose that g of z is now 2 over z plus 1/2, z minus 3/4, and z minus 1. And you should actually be seeing this pole zero pattern as you start to write down that transfer function g of z. How many poles do you have? 3. And how many finite zeros? 0. Not 3. So now we have 0 finite zeros, 3 finite poles, so that our pole zero excess, which is the key property of rule number 4, I was labeling PZ sub E, is 3. Now we can find what the asymptote angles are. The definition is now this 2L plus 1 times 180 degrees all over PZ sub E, where L now varies from 1, 2, and how many more values do I keep evaluating for L? I had PZ sub E as 3. I just need 1 less than that, so I go 0, 1, up to 2. So I plug in 0 for L, I plug in 1 for L, and I plug in 2 for L, and I'll generate all of my asymptote angles, which in this case I have 3 asymptote angles. I have phi sub A. If L is equal to 0, I now have 1 times 180 divided by 3. That gives me this 60 degrees. That's when L is equal to 0. I have another asymptote angle, which is when L is equal to 1, so that's 3 times 180 divided by 3, and that one's pretty clean since the 3's cancel. This is when L is equal to 1. And I have my third asymptote angle, which is now 5 times 180 divided by 3, or now 5/60s. And again, these are all measured with respect to the positive real axis, and this is with L equal to 2. Those are my 3 asymptote angles, 60, 180, and 300. Where are those? These now are pinned or all tied together at one point called the centroid, and we want to know where do we pin that down on the real line. That's our centroid. So the centroid of these 3 asymptotes we have our formula. Sigma sub A is we take all of the poles and add them together, their locations. Where were my poles located? And here, some people were going too fast on the exam, and they were forgetting that maybe with a z plus 1/2, where is that pole actually located? Okay, Wednesday I'm going to bring my steel-toed boots, and we'll have some fun with the front row. Pardon me? Yeah, you can try them on. So we might have a pole now at, or we do have a pole at z equal to minus 1/2. The value of z where that z plus 1/2 is equal to 0. We have a pole at minus 1/2. We have a pole at 3/4, and we have another pole at 1. And you need to use those particular values. We have now the 1/2 plus the pole at 3/4 plus the pole at 1. What did we have for zeros in G of Z? Finite zeros. no finite zeros. That then comes in as nothing, divided by the pole zero excess. Now we have 1/2 plus 3/4, or 1 1/4, 5/4 divided by 3, or we now have 5/12. Or this is now the average of 4/12 and 6/12, or 1/3 and 1/2. So we split that, and we end up with this being 0.4167. That's the centroid. Now we can have a little bit better informed picture of what's going on. We had a pole at 1, we had another pole at 3/4, and we had a pole at minus 1/2. Where are these guidelines? Where are asymptotes? Sigma sub A is at 0.416. So if you're accurately sketching this, you're 41% of the distance between the origin and 1. Meaning you can now say, oh, if this is half, let's say that this is now 0.416. And from that point, I have an asymptote at 60 degrees, 180, which is the negative real line, and 300. Or I can now sketch this. Let's say that's 60 degrees. This is now the mirror image, 300 degrees, and we have another one going off, and that one really doesn't really matter. It's going off to negative infinity. But does this help us sketch our root locus? And the answer is yes. Now what we want to do, which pieces of the real line belong to the root locus? The piece between 3/4 and 1, and another piece to the left of minus 1/2. That one's tracking along the asymptote at 180. The others are going to break away somewhere between the two, not equally spaced because you have that third pole, but it's going to be fairly close actually. And then what happens? Well, now this one goes up and approaches that asymptote, and this one goes down and approaches that asymptote. Is everything fine relative to stability? Can I crank up the gain K as much as I want? Am I initially stable? If I crank up the gain just a little, that pole at 1 will move inside the unit circle. The pole at minus 1/2 will dance a little bit towards minus 1, but all 3 branches will be inside the unit circle. So that now if I had a unit circle, it would look something like that. And I might actually want to know, where do I break away? Because that might inform how I approach those asymptotes. How do I find the breakaway point between 3/4 and 1? And this is a review from exam number 2. No, exam number 3. Have to keep straight. How do we find the breakaway point for this system? Which condition? So now I have 2 conditions that I'm usually playing with on the root locus. A phase angle condition and a magnitude condition. Which of those allows me to determine a formula that I could maybe find the breakaway point between 3/4 and 1? The magnitude condition. I'm trying to find an expression for K, and continue to evaluate that between 3/4 and 1 and try to find the relative maximum of k between 3/4 and 1. And a formula for k is now from the magnitude condition. I know k times g of z. G of z was 2, z plus 1/2, z minus 3/4, and z minus 1 equaling 1. That's from the magnitude condition. I can now solve that for k, and I now have the distance or the length from any point z to 1/2, or z plus 1/2. I now have a length determined by z minus 3/4 and a length determined by z minus 1, all divided by 2. And if I went home tonight and played with this, what would I do? I would plug in different values of z between 3/4 and 1 and be looking for when does k reach a relative maximum between 3/4 and 1. At 3/4, what's k? 0. At 1, what is k? 0. So I'm starting at 0, and as I crank up k, those two closed loop poles are moving towards each other. And when I reach the relative maximum, that's where they will break away and start approaching these asymptotes. I didn't have anything better to do, so I determined that offline. The relative maximum of k is going to actually occur at a z value of 0.881. Is that halfway between 3/4 and 1? It's close, but it's not quite, is it? Because of that pole at minus 1/2. And the k that occurs at, if I now plugged in that k value, or that z value into my k expression, that gives me a k value of 0.011. So now from 0 up to 0.011, I'm living on the real line between 3/4 and 1. But if I get bigger than 0.011, now I'm popping off the real line and approaching those asymptotes. And I'm breaking away at 0.881. What's another quick z value that I could plug in that might inform my thought process relative to determining stability of this system? What's a z value that you just want to plug in? Probably don't want to plug in z equals 0 because it's not even on the real line. I'm sorry, on the root locus. It is on the real line. But what's another value that would be easy to determine and sort of might be suggestive of a possible maximum value for k? It may not be. Pardon? -1. So if we look at z when z is equal to -1, that's when one of these branches is leaving the unit circle. That may be later than when these two branches on the right leave the unit circle, but let's at least find the gain value to get us outside the unit circle on the left-hand side. Since that's pretty easy or clean to determine, we can now say k evaluated at z equal to -1 is going to be -1 plus 1/2, -1 minus 3/4, -1 minus 1, all divided by 2. And now we have 7/8, or a k value of 0.875. So what do we know? We know that we cranked up the gain to 0.011, and we now have already left the real line on the right of this root locus diagram. We crank up the gain quite a bit to 0.875, and that third branch or closed loop pole is leaving along the third branch the unit circle. Probably these two poles that broke away on the right-hand side are exiting the unit circle before 0.875. And if you sketched this accurately, you could eyeball or pretty much measure on your graph paper where that departure point is. If you now have a compass and you draw your unit circle and you've found the breakaway point as 0.88, now you just start zipping off to those asymptotes. You might just guess then that to get us to this point, which I'll say is a triangle, let's now say that here, and let's estimate that to be 0.9, because it's probably a little to the right of where we broke away, which was 0.88. And we could see, maybe if our sketch was somewhat accurate, that maybe we're at 0.43 vertically when we start exiting the unit circle. But we could now plug this value for z into our expression for k and just compute those lengths or those magnitudes. And doing that, we now have z minus 1, z minus 3/4, and z plus 1/2 all over 2 evaluated at z equal to 0.9 plus j 0.43, and that ends up being a number 0.4172. How do we check whether or not that's reasonable for a gain value at that location on the unit circle? How's another way that we could find the answer in the back of the book? We know a K, we have a K. This is much less than 0.875, isn't it? So we know that we can't get to -1 before those two poles on the right have exited the unit circle. If we know a gain K, what can we do with that K relative to this system? And we know we're connected in a negative unity output feedback configuration. If I give you a K, can you tell me something about the closed loop poles? You have to know this by the final. So if I give you a K and you have G and C and everything else, and all you have yet to be determined is K, and now I have one, I've guessed one or calculated one that I think might put me near the unit circle, and I've calculated that to be 0.1472, can I use that K to compute my closed loop poles? And the answer is yes. We know the closed loop poles. For the classical configuration, what's the formula that they satisfy? Kg over 1 plus Kg, where maybe the G is barred. Or the closed loop poles are the denominator of that closed loop transfer function, which now I need to find the values of z that cause that to be true. And I have a K value. In this case now I have 1 plus 2 times K, z minus 1, z minus 3/4, and z plus 1/2, all equaling 0. This you should be able to just stumble out of bed and do on the final. And the final's at 1 p.m., so hopefully you're not stumbling out of bed too much before the final, but that's okay. If rest is an important thing. Now, what are we looking at if we have this equation? We want to find the z's that cause this to be true. But really we're focusing on the numerator of this expression. So if we look at the numerator of that rational expression, we will get our characteristic equation, which now we have z minus 1, z minus 3/4. We're putting everything over a common denominator and keeping the numerator. Z plus 1/2 plus 2 times k, and let's now look at k when k is 0.1472. And now we have to have a way of factoring cubics. Okay, but we have a good idea where those are just from our sketch. But if we calculated that, the roots of that cubic, we would find that we end up with a root being at 0.94 plus and minus j 0.42, and another one at minus 0.631. What are we interested in relative to these complex numbers? We had 3 roots. We should have expected one to be real, at least. We could have had 3 real roots, but if we have one real, then we have a pair of complex conjugate, and that's what we have. How does this compare to what we thought we were doing? 0.9 plus j 0.43. This one's a little bigger, isn't it? It's 0.94, so it's bending over to the right maybe a little faster than what we had anticipated from our sketch. And if we found the magnitude of this, it's actually beyond the unit circle. So that k is a little bit too big for stability even. That gain of 0.1, whatever it was, 4.1472 is a little too big to preserve stability. Just to be conservative, we might just say, well, let's just assume then that the upper bound for stability is not 0.147. Let's even say it's not 0.14. Let's back off a little bit more and say it's 0.11. So let's just say if I have a dial on K, I'm only going to go between 0 and 0.11 to be stable in this particular system. So let's just say that this is now the stable upper bound. And do you see that you could start to iterate on K in this expression and then find the roots and generate when am I actually having a set of complex poles that have a magnitude of 1? Yes? So now the question was, how did I find this value of z, I think? So here I found it numerically. I didn't want to differentiate a cubic and then set that. You could. That would just end up with a quadratic, and that would be doable. But if this was now a 4th order, then you would have to factor a cubic, and I might not want to do this. It's not too bad to just be evaluating this expression for k between 0 and 1, and you might start halfway between that. I'm sorry, not 0 and 1, 0.75 and 1, halfway between that, and going one direction or the other and seeing, am I still increasing? Am I still increasing in k? And then I start to roll off. Then I've hit my sweet spot. Then I found the z value where k is a relative maximum. That's what I would have done, is I would have plugged in numbers for z in this formula and just tried to find which of those. So if I now looked at z of 0.89, hopefully my k is less. And my k for that value I calculated to be 0.011. And if I calculated the k at 0.87, hopefully that is less than 0.011. So it's not so, it is trial and error, but it's a guided trial and error because you know that you're searching for this bump. It starts at 0 at 3/4 and 1, and you're just continuing to increase, and you're looking to find where do I reach that relative maximum. That's my Z value that is the breakaway point. Yes, so if you graphed, the question was if I graphed this, you could now find the relative max of that graph, and that value of Z where you reach that relative max should be your breakaway point. And your calculators can do that for you if you want. Some of them can. Now, what if we did the following? Suppose we know the upper bound for a system to be stable is a K value of 0.11. Suppose we pick K of 0.011. What's that going to give us? Do you remember what a K value of 0.011 was? That was our breakaway point. And what happens at the breakaway? How many real poles do we have? 3. Now the 3 comes back into play. We have 2 right on top of each other at 0.88, and 1 is off between -1/2 and -1. So let's now pick, or suppose we pick a K of 0.011, and that now is going to produce 3 real poles. What's my dominant pole? What value of Z is my dominant pole? No hints at all. I have a gain K of 0.011, and I want to know where are my 3 poles? You have 2 at 0.88. Where's your other one? Between -1/2 and -1. That's going to be bouncing around. That's not going to dominate your behavior. So we're going to now have, this is our biggest one, with a Z value of 0.881. Can you tell me anything about the settling time if you have a dominant pole of 0.881? And don't tell me you forgot everything you did on exam number 3 over the weekend. This is an exam 3 problem. The 1% settling time is there. Buried in, not buried, but it's in that equation. What do you know? You know R, you're just trying to find N sub S, and you can solve that for N sub S. So that N sub S is now -2 log base 10 of R And now we know that our system will settle in 37 sample periods. And as an engineer, you're going to be taxed with taxed, I shouldn't have said that. Taxes are due tomorrow, right? Late nights for some of us. But is that too slow, 37 samples? What if it is? What if your boss says, that's just too slow, I can't wait 37 samples? Hopefully that didn't come through on the microphone. You're not out of luck. What would you maybe do? You may not want to crank up the gain, because what's going to happen? You move from that point. How are those dominant poles varying relative to their magnitude? They're going away from the origin, aren't they? So now your radius is getting bigger. You're getting slower. You might get faster in terms of peak time, but now in terms of settling time, you're not really getting any faster than that. So we're going to have to change dramatically the structure of this pole zero pattern for the closed loop poles. We've already looked at PI, which deals with steady state accuracy. Maybe we need to introduce a derivative action via the PID controller. That's motivation for learning how to play with PID controllers. That will be next time. Let's look at rule number 5. Do we always have departure angles and arrival angles? No, we might only have arrival angles. We may only have departure angles. It depends on how many complex poles and zeros you have. Let's look at an example. Suppose that we now have a numerical example in the following form. Suppose g of z is now 2 z minus 1/2 over z minus 1 squared plus 1/2 squared. We have a finite zero where? Negative 1/2 or 1/2? It's at 1/2. It's right there. We have we have poles, open loop poles, at a real part of 1 and an imaginary part of 1/2. Are those outside the unit circle? Yes, they are, aren't they? Because they have a real part, a horizontal of 1, and then some vertical equaling 1/2. So the hypotenuse is bigger than 1. So we are outside the unit circle. If my sketch was anything accurate, there's our unit circle. And what's the root locus going to look like? This one actually you can do based on what you've already done with 2 poles and a 0. Another TV show. 2 poles and a 0. You know the radius. You could measure the radius from that 0 to those poles. And you could bring those down to be on the real line, but in fact, once you have this radius, you can now use your compass and you could sketch this. So this one didn't even really need rule number 5 to determine the departure angle. But we're now trying to find what's alpha sub d? What's the departure angle? Which means that if I'm on this root locus a short distance away from, and here it's an epsilon distance, I'm basically right on that pole, but I want to be a little bit off so that I have an angle from that pole to that dot, but all the other poles and zeros I can effectively be right on top of that pole. I now want to know what is alpha sub d. I want to know what is this angle, theta sub z, and what is this angle from that pole to the pole right above me. Because I know that if I'm on the root locus, what do the angles have to sum to? Minus 180 degrees. The phase angle condition now tells me that the angle of my poles and zeros of g of z need to sum algebraically to minus 180. Or that's now saying that I have the angle of the zero factor minus the angles of my poles. I have an angle at z minus 1 minus j 1/2. That's the pole in the first quadrant, and I want to find its angle, plus the angle z minus 1 plus j 1/2. At that point, let's say that green dot that's infinitesimally close to that pole in the first quadrant. I need to find those angles, and which angle is unknown. If you have your protractor, you can measure the angle from the zero to the pole. And actually, you can numerically figure that out. You're 1/2 over and 1/2 up, right? So the angle from the zero to that pole is 45 degrees. We also know what the angle from the lower pole to the upper pole is. We just have to look straight up. That's 90 degrees. So that now we have minus 180 is equal to the angle of the zero minus the unknown, the angle that we're departing that upper pole in the first quadrant, plus the angle of the pole to that pole in the first quadrant, which we're calling theta sub p sub 2. And we just determined some of those values. Theta sub z was 45. Alpha sub d, we maybe don't know, but what's theta sub p sub 2? That's 90 degrees. Bless you. So our only unknown is what? We now have minus 180 is equal to 45 minus alpha d minus 90 degrees. Or alpha sub d is 180 plus 45 minus 90, or 135 degrees, which is what we sort of knew from our earlier knowledge of the root locus diagrams. We know that we're departing at an angle of 135 degrees from that pole in the first quadrant. And that now helped inform our sketch of the root locus. The root locus now leaves the two poles. One goes to the finite zero at 1/2. The other one marches off to minus infinity. Why do we know that? What's our pole zero excess? 1. What's the asymptote angle? The fundamental is always 180 divided by the pole zero excess. So 180 divided by 1 is a hard calculation. It's 180. So we have one asymptote, and it's going off to minus 180. How could we find this triangle location? Could we? Law of cosines. Because we know the radius, we can find the different distance from that zero to the pole and find its magnitude. We have, if we called this point P1 and this point Z, and this, let's say, is R, we know that Z plus R is equal to P1 vectorially. Yes? So that now R is just P1 minus Z. And if we wanted to know the magnitude of R, we could just find the magnitude of that complex number. And we know P1 was at 1 plus J 1/2. Z was 1/2. We now know that radius. We also know this length. From the origin to Z, that's 1/2. What's this distance? This distance is R. From the origin to the triangle is 1 because it's on the unit circle. We know all 3 sides lengths of that triangle. And we can now use that to find this unknown angle, if we wanted to guide that choice of that triangle location. Now, you've drawn this on the back of an envelope. You have a good feel for this, but you want it to be a little bit more precise. What might you do? Well, you might open up your computer and get into MATLAB, right? If you were in MATLAB, you could just say R locus G, and it would sketch the root locus. Now, that's assuming that G has been defined. G is now a transfer function. What was this particular system? It was 2 times 1, comma, that's the numerator. What's the denominator? We could just multiply it out, right? We have z squared minus 2z plus 1 plus 1/4. So that now we have our denominator is going to be 1 minus 2 and then 1.25. And if this is a z transform, if this is the z domain and we don't know the sample period, we would say comma minus 1. Now we have a transfer function with an unknown sample period. It's a discrete time system. We could now say R locus G, and if we wanted to poke around with our mouse, we could actually tell MATLAB to try to find us points with our mouse as far as what's the gain at that particular point. And it will now give us the gain value at that point on our root locus diagram. And this is a way that you could check your work with answers in the back of the book indirectly through MATLAB. Questions on this? Well, if you don't tell it minus 1, then MATLAB will assume this is a continuous time transfer function. TF is smart, but it's not that smart. It doesn't know whether this is continuous time or discrete time. If you knew the sample period, and let's say you knew the sample period was 0.01, you would put comma 0.01. If you don't know the sample period, but you want MATLAB to know that I'm playing with a discrete time system, you put comma minus 1, saying this is an unspecified sample period. So it will draw the same root locus, but now if you started to say something like grid, it would give you the wrong grid on your frequency domain plot. So now you kind of want MATLAB to know whether you're dealing with continuous time or discrete time system. We'll pick up later on that.